this class, we'll be seeing the frequency domain representation of the AM wave. So for that, we just revise some Fourier transform of some basic functions. We know that the Fourier transform of a constant is given by delta function. It is defined only at f equal to 0, and for all the remaining frequencies it will be 0. Coming to the Fourier transform of cos 2 pi fct. So this cos signal can be expressed as expressed in terms of exponential function as shown here. So it can be expressed as e power minus j 2 pi fct plus e power j 2 pi fct by 2. So in order to find the Fourier transform of this term, we use frequency shifting property. So if the Fourier transform of constant is delta function, so if we multiply this constant 1 by 2 by e power minus j 2 pi fct, so the Fourier transform will be this del of f shifted in frequency by fc. So this has been obtained by using frequency shifting property. Similarly, for this term, the Fourier transform will be delta function shifted in frequency plus fc. And let's say that the Fourier transform of the message signal or modulating signal is capital M of f. Then Fourier transform of this function m of t into cos 2 pi fct can be expressed as shown here. So this has also been obtained by using this frequency shifting property. So as we can write this cos in terms of exponential function. So when this m of t is multiplied by this exponential function by using frequency shifting property, the Fourier transform will be m of f minus fc. So whenever this term m of t is multiplied by an exponential function in frequency domain, it will be shifted in frequency by fc. So the Fourier transform of m of t into cos 2 pi fct will become 1 by 2 into m of f minus fc plus m of f plus fc. From the Fourier transform of these basic functions, now we can find out the Fourier transform of standard AM wave. As we have seen already, the standard AM wave is defined by using this equation. So simplifying it, we get AC cos 2 pi fct plus AC into Ka m of t into cos 2 pi fct. So to determine frequency distribution of this AM wave, we take Fourier transform of both the sides. So the Fourier transform of this modulated waveform s of t becomes s of f, and this Fourier transform of this first term, that is cos signal, will be, as we have seen, the Fourier transform of cos function is delta function shifted in frequency. So it will be AC by 2 del of f minus fc plus del of f plus fc. And coming to the second term, the Fourier transform will be, so this will be constant AC Ka, so it will be remain as it is. And as we have seen, when the message signal is multiplied by cos signal, the spectrum will be 1 by 2 times f minus fc plus f plus fc. So this will be the frequency domain description of AM wave. So here m of f is the Fourier transform of message signal mp, and here the message signal is band limited to the interval minus w to w. That means the message signal will be occupying the frequencies from minus w to w, and as we know that the carrier frequency is always greater than the message signal frequency. That is the reason why we are going for modulation, because we want to translate this low frequency message signal to a higher frequency. So the fc value will always be greater than w. So let's say that this figure 1 shows the Fourier transform of message signal. So it is denoted as m of f and plotted on the frequency axis. So as we have seen that m of t is band limited to the interval minus w to w. So the spectrum will be occupying the values from minus w to w, and at f equal to 0, it will have maximum value, which is m of 0. So this is the frequency spectrum of message signal. So if this is the spectrum of message signal, then this figure 2 shows the spectrum of AM wave. So if we observe the equation here, so it is having 4 different terms. So the first term is AC by 2 into del of f minus fc. So that means we'll be having the spectrum at f equal to fc. So we will be having magnitude when this delta function is equal to 0. So this will become 0 when f equal to fc. So at f equal to fc, we have AC by 2. So this is the first term, AC by 2 into del of f minus fc. And the second term is AC by 2 del of f plus fc. So this will be having it f equal to minus fc. So this will be the frequency spectrum of the second term, AC by 2 del of f plus fc. And coming to the third term, the third term is Ka AC by 2 into m of f minus fc. Since this is the spectrum of m of f, so if we shift this spectrum to the frequency value fc, so this spectrum will be centered at fc instead of 0. So since m of f is centered at 0, m of f minus fc will be centered at f equal to fc. So if we shift this spectrum to the right, so this will be the spectrum, and this amplitude value will be 1 by 2 Ka into AC. And the last term, that is the fourth term, will be at f equal to minus fc. So this will be the spectrum. So again, the same spectrum is shifted to the left to the value of minus fc. So this is the spectrum of the fourth term. So since this is the spectrum is band limited, so this higher frequency will become fc plus w, and this frequency will become minus fc minus w. Similarly, at the negative side, this will be minus fc plus w, and this will be minus fc minus w. So if this is the spectrum of message signal, so the spectrum of AM wave will have 4 terms. First one is del of f minus fc. The second one is del of f plus fc. The third term is m of f minus fc, and fourth one is m of f minus fc. Spectrum consists of 2 delta functions weighted by the factor AC by 2, occurring at plus or minus fc. So that is the delta functions at plus or minus fc with weight AC by 2, and 2 versions of baseband spectrum translated in frequency by plus or minus fc. So this baseband spectrum is translated in frequency by plus or minus fc, and with weight Ka AC by 2, scaled in amplitude by Ka AC by 2. So for positive frequencies, the portion of spectrum lying above the carrier frequency is called upper sideband. So the frequencies above the carrier frequency fc is called as, the band is called as lower sideband, and the band which is less than this carrier frequency is called as lower sideband. That is, the symmetric portion below fc is called lower sideband. And here the condition fc greater than w ensures that the sidebands do not overlap. Otherwise, the modulated wave exhibits spectral overlap, and therefore frequency distortion will occur. So here, as said, the frequency fc should be always greater than w. Otherwise, if this value is not greater than w, then these lower sidebands might overlap with each other. And for the positive frequencies, the highest frequency component of AM wave is, so this is the highest frequency component, which is fc plus w, and the lowest frequency component is fc minus w. So for positive frequencies, highest frequency component is fc plus w, and lowest frequency component is fc minus w. So in order to calculate the bandwidth, so we take difference of these two waveforms. Difference between these two frequencies will give us the transmission bandwidth, which is exactly twice the message bandwidth w. So since we will be calculating the bandwidth considering only positive frequencies, so the message signal is having bandwidth from 0 to W, that is the bandwidth is W, and coming to the AM wave, the bandwidth will be Fc plus W minus Fc minus W, which will be 2W. So the bandwidth of AM wave is exactly twice the bandwidth of message signal. We observe this spectrum. The spectrum of the AM wave is full, means it consists of the carrier, the upper sideband, and the lower sideband. So if we observe the spectrum, we have the carrier, upper sideband, and lower sideband. So this is the reason why we call this form of amplitude modulation as standard AM modulation. Why we are telling it as full is because we have one more modulation called DSB-SE, means double sideband suppressor carrier. So in that, what we will do is we will be removing the carrier, and we also have single sideband AM modulation. So we will be discussing them in the next lectures. So this form of AM is called as standard AM because it is having all the carrier, spectrum, upper sideband, and lower sideband. So, let us say that this is the spectrum of message signal, that is M of F. So which is having bandwidth from 0 to W, and this will be minus W. So if we plot the spectrum of AM wave, that is S of F. So here the first term is del of F minus Fc. So it will be having delta function at F minus Fc equal to 0. That is at F equal to Fc. So we will be having delta function at F equal to Fc of amplitude AC by 2. So a delta function of amplitude AC by 2. Similarly, the second term, so this will be having delta function at F plus Fc equal to 0. That is at F equal to minus Fc. So this is Fc. And similarly, we have another delta function at F equal to minus Fc of amplitude, again same, AC by. So now we have drawn the spectrum of these first two terms, and the third term is Ka AC by 2 into M of F minus Fc. So since this is the spectrum of M of F, so M of F minus Fc will be having the same spectrum at F equal to Fc. So this spectrum will be shifted to the right by Fc. So since it is being shifted to the right, so since the maximum value is W, so here this corresponding value becomes Fc plus W, and this lower term becomes Fc minus W. And coming to the fourth term, okay, and this amplitude will be Ka AC by 2. And coming to the fourth term, so it will be having this same spectrum at F equal to minus Fc. So it will be repeated here. So here this upper limit will be minus Fc plus W, and this lower limit will be minus Fc minus W. So this is how we have plotted the spectrum of AM wave. So in order to calculate the bandwidth, this will be the bandwidth. So we'll be calculating for only positive frequencies. So bandwidth of message signal is W, and the bandwidth of this AM wave is Fc plus W minus this lower limit, that is Fc minus W. So Fc will be cancelled out and we will be having bandwidth of 2 into W. So if we modulate a message signal of bandwidth W, so the modulated signal will have bandwidth which is equal to twice the bandwidth of message signal. And then we have also seen that this Fc value should be greater than W. So let's say that if Fc value is not greater than W, so what will happen here is so now if we draw the spectrum, since Fc is less than W, let's say W is over here. So if Fc is somewhere over here, so the spectrum will look like this. This is Fc, and this will be Fc plus W, and this will be Fc minus W. So since here, if we are taking Fc less than W, so this value Fc minus W will become negative value. So it will be crossing the zero value, and similarly the other spectrum will look like this. So if Fc value is not greater than W, so these so as I said, this is the lower sideband. This is also lower sideband. So the lower sidebands will be overlapped here. So if Fc value is less than W, so these spectrums will overlap with each other and there will be a distortion in frequency domain. So that is the reason why this Fc value should be always greater than W. So now we will see single tone modulation of AM. So here we are considering one example. So till now we have not taken any message signal. In general, we have discussed the frequency spectrum. Now by taking an example of single sinusoid, so here by considering modulating wave as AM cos 2 pi FMT. So it is called single tone modulation because this is having only single frequency component. So now the AM wave is described by this equation, AC into 1 plus Ka M of t. So M of t is replaced by this quantity AM cos 2 pi FMT. So now if we represent this as shown here, AC into 1 plus mu. So this Ka into AM is represented by mu, which is known as modulation factor. So this will be the AM wave for single tone modulation. So as we have discussed earlier, to avoid the envelope distortion, this Ka AM value should be less than 1. That means the modulation factor mu should always be kept below 1. And let us assume that A max and A minimum be the maximum and minimum values of this envelope. So if A maximum is the maximum value and A minimum is the minimum value, so in order to find the maximum value, we can replace this cos function by its maximum value, which is plus 1. So the maximum value becomes AC into 1 plus mu. Similarly, to find the minimum value, replace this cos function by minus 1. So the minimum value will be AC into 1 minus mu. So if we consider the ratio A max by A minimum, so it will be AC into 1 plus mu by AC into 1 minus mu. Since here the cos function maximum value is plus 1 and here the minimum value of cos function is minus 1. So this will be the ratio of A max by A minimum. So now if we simplify this by taking A max minus A min by A max plus A min, so we will get 2 mu by 2, which is equal to mu. So from this we will get the modulation factor as A max minus A min by A max plus A min. So now considering this time domain equation of single tone modulation and simplifying it further, so we will get this first term as AC into cos 2 pi FCT, and the second term will be AC into mu into cos 2 pi fmt into cos 2 pi fc2. So now by using the relation cos A into cos B is equal to 1 by 2 times cos A plus B plus cos A minus B. So by using this relation over here, so we can simplify this further as, so this first term will remain as it is, and the second term becomes AC mu by 2 cos A plus B. That means the sum of these two frequencies, 2 pi into Fc plus Fm, and the second term will be A minus B, that is difference of these frequencies. It is cos 2 pi Fc minus Fm. So we are taking Fc minus Fm because Fc is always greater than Fm. So this will be the simplified time domain equation of single tone modulation. So again, in order to plot the frequency domain description, so by taking Fourier transform of this equation, we'll get this equation. So again, as we know, the Fourier transform of cos function is expressed in delta. So this will be AC by 2 del of f minus fc plus del of f plus fc. So coming to the second term, so it will be AC mu by 2. Already 1 by 2 is there. So again, if we take 1 by 2 times del of function, so it will become AC mu by 4. So since here the frequency is fc plus fm, so here the delta function will be shifted by fc plus fm on both the sides. And similarly, for the third term, the frequency will be fc minus fm. So hence the spectrum of this AM wave will have, which is special case of sinusoidal modulation, it will have delta functions at plus or minus fc, fc plus or minus fm, and minus fc plus or minus fm. So if we plot them, so here instead of general message signal, we are taking a cosine signal of frequency fm. So for a cos signal, if we present it in frequency domain, so it will be having two delta functions, one at plus fm and other one at minus fm. So similarly for the carrier signal, so it will be having two delta functions at plus fc and minus fc. So for the modulated signal, so we'll be having these frequency terms. The first one are the frequency components of plus or minus fc, and then the same message spectrum shifted in frequency by fc. So when this spectrum is shifted to the right by quantity fc, so this spectrum will be plotted over here. So this will be, so since it is being shifted to the right by fc, so it will be centered at fc, and this upper limit will become fc plus fm, and this lower limit becomes fc minus fm. And coming to the last fourth term, so again the same spectrum is shifted to the left, so this will be centered at minus fc, and the upper limit becomes minus fc plus fm, and the lower limit becomes minus fc minus fm. So again here the bandwidth of message signal is fm, and the bandwidth of this modulated signal becomes 2 times fm. So this is the special case where we are considering a single sinusoid as the message signal.